This resource focuses on giving worked examples with the quotient rule. So previous videos then have given a definition and a concise derivation of differentiation from first principles. And now we want to give a number of worked examples. In this resource the focus is on the quotient rule, and we're going to use that in combination with a table of results for simple functions. So here's the quotient rule. If y is given by u of x over v of x, then the derivative dy dx is given by v du dx minus u dv dx over v squared. And this resource will just focus on a number of examples using this rule. We're going to exploit a table of common results, so it's assumed that students have access to the derivatives of simple functions, so things like ax, ax to the n, cos bx, e to the cx, and so on. How are we going to do this then? There's a key technique that you should deploy to keep things simple and correct. First of all, define all the functions used in the quotient rule with their associated derivatives clearly. Ensure the layout of your work is uncluttered and unambiguous, and this will help you avoid many typos. And wherever you can, use known results from a table. So 3 simple pieces of advice that should make solving the derivatives straightforward and reduce the number of errors apart from typos, which happens to anyone. First example then. Find the derivative of y given by 2x to the 4 plus x over cos 5x. And we're going to use the quotient rule, which you'll see I've put up here in the top right, just so we remember what it is. So the first thing we've got to do is clearly define u of x, v of x, and the associated derivatives, which we need in this rule up here. So u of x is given by 2x to the 4 plus x, and du dx is therefore going to be 8x cubed plus 1. V is given as cos 5x, so dv dx is going to be minus 5 sine 5x. So those 2 derivatives straight from the table. And now all I do is plug these results into the formula. So what are we going to get? dy dx equals, so we can put a big line here. So first of all we get v, so that's cos 5x, times du dx, so that's times 8x cubed plus 1, and then we get minus, and then u, so that's 2x to the 4 plus x, times dv dx, which is minus 5 sine 5x, and all divided by v squared, so we've got cos squared of 5x. Now it's recognised you can simplify this a little bit. Clearly there's 2 negative signs which will cancel, but as a general rule I wouldn't bother multiplying this out. I would leave it in this form. Next example, find the derivative of 3 sine 2x plus tan 3x over e to the 0.4x. So again, our first step is to define u, v, and du dx and dv dx clearly. So u, which is the numerator, is 3 sine 2x plus tan 3x, and therefore du dx is going to be 6 cos 2x plus 3 sec squared 3x. So that's covered from the earlier videos, or just taken straight from the table. Similarly, v equals e to the 0.4x, so dv dx is 0.4 e to the 0.4x. And now all I do is plug those answers into the formula for the quotient rule at the top. So therefore, dy dx equals, so again put a big line so we know what's going, so we start with v, which is e to the 0.4x, multiplied by du dx, so I get 6 cos 2x plus 3 sec squared 3x, I missed an s in there, and then you're going to get minus, and then we get u, which is 3 sine 2x plus tan 3x, all divided times by dv dx, which is 0.4, so I've run out of space, e to the 0.4x, and then all divided by e to the 0.4x squared. Example 3. Find the derivative of y equals log of 2x cubed over x to the 5 plus 4x plus 1. And by now, you'll see what the technique is. First, we define u, but what I've done here is I've said, look, I can simplify this u, using the powers of logs, or the rules of logs. So log of 2x cubed is log 2 plus 3 log x. And the advantage of doing that is the derivative is now much more obvious. So the derivative is just du dx is 3 over x. V, x to the 5 plus 4x plus 1, so this is a standard polynomial, so the derivative is 5x to the 4 plus 4. And now again, all I do is plug these answers into my standard formula up here. So dy dx equals, and we start with v, so I've got x to the 5 plus 4x plus 1 times du dx, which is 3 over x, and then minus, and then we get u, so that's log, and you can put the 2x cubed back in if you like, because it's just u, as you please, and then times dv dx, which is 5x to the 4 plus 4, and then all divided by x to the 5 plus 4x plus 1 squared. And again, you'll see I'm not trying to simplify these expressions, I'm not trying to multiply them out, because often that actually makes more of a mess and doesn't simplify things at all. So often it's better just to leave it in this form until you know exactly what you want to do next. Okay, some special cases, the inverse of trigonometric functions and the inverse of polynomials. So we'll start with polynomials. How would you find the derivative of something like 1 over x to the n using the quotient rule? So we'll use the standard technique. First we'll define u, which is 1, and then du dx is clearly 0. We'll define v as x to the n, so that dv dx equals n, x to the n minus 1. So now all I need to do is plug those into the formula, and you'll see I get dy dx equals, so v, n x to the n minus 1 times du dx, so that's times 0, and I've made a silly mistake there, and that happens, I do apologise, let's write that again. So v is x to the n, and du dx is 0, and then I'm going to get minus u, which is 1, times dv dx, which is nx to the n minus 1, and then all divided by x to the 2n. Now what you'll see here is clearly this term's a 0, so it can disappear. And the next thing you'll notice is that I've got an x to the n minus 1 here, and an x to the 2n here. So if I cancel missing terms, I'm going to get, cancelling terms, I'm going to get minus n over x to the n plus 1. So that shows you that the power of x has decreased by 1 because the denominator power has increased by 1. Standard results then. So we've obviously just done one example, but the key thing is you'll see things like dy dx of 1 over x is minus 1 over x squared. Dy dx of 1 over x squared is minus 2 over x cubed. Dy dx of 1 over x cubed is minus 3 over x to the 4, and so on. What about trigonometric functions then? Find the derivative of 1 over sine x. So again, we'll define u and v, and just progress in a methodical fashion. U equals 1, du dx equals 0. V equals sine x, so dv dx equals cos x. And again, I just plug these into the formula. So dy dx equals v, which is sine x, and that's going to be times du dx, which is 0, and then minus u, which is 1, times dv dx, which is cos x, all divided by sine squared x. And obviously the term that's multiplied by 0 disappears, so you end up with minus cos x over sine squared x. What about 1 over cos x? Well, this is going to be very similar. Again, you'll see u is 1, du dx is 0. V is cos x, so dv dx is minus sine x. So I can now write down that dy dx equals, we're going to get 0, I won't bother writing it out in full, and then minus, and then we're going to get 1 times minus sine x, all divided by cos squared x. And you'll see in this case the two minuses cancel, so you'll get sine x over cos squared x. Example 7. What about 1 over tan x? Well, here again, u is 1, du dx is 0, v is tan x, so dv dx is sec squared x, or 1 over cos squared x. You can choose depending upon how you want to write the answer. So dy dx is again going to be a 0 term, which I'll ignore, and then I'll get minus 1 times sec squared x, all divided by tan squared x. And you can simplify that if you want, but it's not the purpose of this video to look at that. So in summary, this video has demonstrated the differentiation of commonplace functions using a lookup table in combination with the quotient rule. And viewers will see the steps are largely mechanical, albeit tedious at times, and the expressions can end up being quite messy, but that doesn't really matter. What you should do is keep clear definitions of u of x, v of x, and their derivatives, and then just substitute them into the formula. In general, it's advisable to have a lookup table to hand, even though in due course you are likely to remember many of the results.